Today we'll continue with Newton's second law, but we'll introduce an additional force to consider. So we talked about the types of forces that you might think about as you're constructing a free body diagram last time. Friction is a new one, and because it's a little bit subtle, we're going to talk about what the frictional force is, meaning what is its magnitude and direction. And it turns out there's actually two types of frictional forces, so we'll talk about both of them. And then we'll do two examples that sort of illustrate them in action. Okay, so first an overview, and I should say that you should look at your lecture notes and the textbook for a full description of these frictional forces, because here I'm just going to present sort of the essential parts of them. So the first thing to say is that there are two distinct types of friction, and you might not have known that already, but once I describe what they are, I think you'll be familiar with both of them. So one is called kinetic friction, and kinetic friction is the friction due to the relative motion of objects. So due to relative motion of objects. And you might also call that rubbing friction. So when two objects rub up against each other, then there's a frictional force. And you should be familiar with this. If you just take your hand and slide it across the table in front of you, you'll notice that there's a resistance to sliding. That's the frictional force. The other type of friction is called static force, and that occurs when there is no relative motion of objects, and in fact it prevents, prevents the relative motion of objects. So going back to your hand on the table, it should be that if you press hard enough down and apply a small enough force to try and get your hand to move, that you'll see that it doesn't move. So even if you apply a force with your wrist on your hand to try and make your hand slide across the table, you'll see that it does not. And that's the force of static friction that prevents it from moving. And they're two different things, but they do share a number of qualities. So one is they're both contact forces, so they both occur so connected to a normal force. So normal force is the force of contact between two objects, but whereas the normal force points perpendicularly to the surface of contact, each frictional force points parallel to the surface of contact. So in fact, sometimes frictional forces and normal forces are simply joined together into a single contact force, which then could point in any direction, but we'll always separate them. So here's a snowboarder on the snow, and that green line that I drew is the surface of contact between the board and the snow, and we know already that if you draw a perpendicular, then there's going to be a normal force on the snowboard or on the snowboarder that points like this. But if the person is sliding down the hill with some velocity that goes that way, then that means that the person is in relative motion to the hill, so meaning the snowboard is in motion relative to the ground, and that will mean that there's a frictional force. Which type of frictional force is this going to be? Well, it's going to be a kinetic frictional force because they are in relative motion. The two objects are in relative motion, meaning the snowboard and the ground are in relative motion. If the snowboarder had just sort of gone a little ways up the hill and then sat on their snowboard, you may have done this if you go snowboarding, then it's possible to not be moving even though you're on an incline, and in that case there would be a static frictional force preventing you from moving. How do you move? Well, you break the static frictional force. So either you go on a larger incline or you sort of jimmy your snowboard a little bit to break that contact. Once you do that, then you can start to move, and we'll see why that's the case. So those are the two types of forces. So let's take them one by one and just give a few more details. So kinetic friction is the force of friction when two objects are in contact. That means that there's a Newton's third law action-reaction pair of normal forces on the two objects. And they're in relative motion. So each exerts a frictional force on the other. And of course, these frictional forces are also a Newton's third law pair. So if we just go back and look at the snowboarder, the object that we're drawing here is the free body diagram for the snowboarder, or maybe for the snowboard. The Newton's third law pair would be the ground. And if there's a force of friction of the ground on the snowboard, then there should also be an equal but oppositely directed, or maybe better just to say an opposite force of the snowboard on the ground. They should be equal in length. So I guess I should write this as the force of friction ground on snowboard, and this is the force of friction snowboard on ground. So it's important to remember that there are these Newton's third law pairs. However, primarily we'll deal with frictional forces acting on a single object. So we'll just think about the ground as some fixed stationary object which exerts a force on other things that are sliding across it. But of course there is a force, there is a Newton's third law pair. So kinetic friction occurs when these objects are in motion, and the magnitude of it is given by this equation here. So what does that mean? Well, first of all, we should say what these are. So this is a constant, and it's a constant which is due to the properties of both objects. So it's something about the way that the two objects interact that determines this constant. And what we mean that it's constant is that it doesn't change, for instance, depending on the relative velocity of these objects. So even as you're speeding up, the force of friction will remain the same as long as everything on the right-hand side of this equation remains the same. And as we described above, the normal force plays a role here. So if you take your hand on the table again, if you just put your hand lightly on the table, you should be able to push it so that it slides. Then as you press further down on the table, meaning that the normal force of the table on your hand gets larger, then the normal force gets larger, and therefore, because of this equation, the frictional force gets larger. And at some point, you won't be able to move it, and then it will convert to static friction. But just for kinetic friction, when they're in motion, there's a constant value, mu k, that determines the magnitude of the frictional force. And we'll do that in an example. So the direction of the frictional force is opposite to the relative motion. So opposite to the velocity of the object. So we saw that up here with the snowboarder, where we had the snowboarder is moving down the hill, and the force of friction of the ground on the snowboard is opposite to that velocity. That's for kinetic friction. So let's just do one quick more example. If you're dragging a box across the ground, so maybe here you are pulling on the box, well then there's a force of tension of you pulling on the box. There's a force of gravity because the box has mass. There's a normal force. And if we say that there is a non-zero mu k, so this is the Greek letter mu, if we say that there's a non-zero mu k, then that means that there will also be a frictional force because there is a normal force. So if there's a normal force and there's some positive mu k value, then there will be a frictional force. And that frictional force will oppose the velocity of the object. So it looks to me like in this picture, the object is moving in that direction, and therefore there is a frictional force which will point backwards. Maybe I shouldn't have drawn it so long. Let's just draw it a little bit shorter. So this is the force of friction, kinetic. We draw it. One thing I think I left out is that this mu k is called the coefficient of kinetic friction. So let's just state that off to the side. Coefficient of kinetic friction. So coefficient just means that it's the thing that multiplies the normal force here. So that's one example of the force of kinetic friction. We could use the same example and get a smaller force of kinetic friction. So how do you make a smaller force of kinetic friction? Well, there's two ways. One is that mu k could change, but if we use the same example, then the box doesn't change, the ground doesn't change, so mu k is a property of those two objects, it's not going to change. The other way to make the force of kinetic friction smaller is to make the normal force smaller. So how can we do that? Well, in this case, the normal force and the gravity force are the only things in the y direction. So when you add them up in Newton's second law, in the y equation, you'll find that the magnitude of the normal is equal to the weight. Well, I could make the normal smaller by adding another force in the y direction. So how could we do that? Well, let's draw it. Let's say that a little bit further down the road, you get smarter and you decide to stop slouching, and you decide to pull with an angle. So now we have a tension force that has a y component, and then we have still the normal force, but maybe it's smaller. We still have the gravitational force, and then we'll get a frictional force, but the frictional force will be smaller. Still force of friction kinetic. So how do we see that? Well, if you look in the y direction, what are the things that are acting in the y direction? Well, we still have force of gravity downward, but that's going to be, since there's no acceleration in the y direction, because if there's any acceleration, it must point along the ground here. If there's any, there's no acceleration in the y direction, the y component of this vector is 0, then it must be that the y forces add up to 0. Or I should say the y components of the forces add up to 0. So gravity points down, so that might be a negative y component, and that will be balanced by not just the normal force, but also the y component of the tension force. So over here, I guess I should have drawn my gravity a little bit more. Gravity wasn't supposed to change here. So over here, the normal force and the gravity force were equal because they were the only things balancing in the y direction. But over here, we have a downward gravitational force and then two upward forces, and they would sum to the magnitude of the force of gravity. So because the normal force got smaller in this picture, the frictional force also got smaller. And that's just like when you're sliding your hand across the table, you sort of lift it off a little bit, and that force will be less. The second frictional force is the force of static friction. And so this force occurs when there are two objects that are in contact. So again, you have that pair of normal forces of one object on the other, but they're not moving with respect to each other. And if that's the case, well, it could be that you just have two objects in contact and there's no static frictional force. So if you just put a book on a table, then you wouldn't expect any horizontal forces at all. But they could exert a static frictional force, and that occurs when they try to resist relative motion. So if you place a book on a table and then you take your finger and you press lightly on that book, the book might not move, even though you're applying a force. And that's because there will be a static frictional force that opposes the attempt to give them a relative motion. So we'll see this in examples, but the statement of the magnitude and the direction are that we don't know the magnitude, meaning that it needs to be found through Newton's second law, because, as we said, it resists the motion, so it's basically whatever is needed to maintain that zero velocity. However, there's still what we call a coefficient of static friction. So that's mu s. And it still has sort of the same form on the right-hand side of this equation, but if you look at the left-hand side, it's different than what we saw for the force of kinetic friction. So the magnitude of the force of kinetic friction at all times is just mu k times Fn. That's for a sliding object. But for static friction, you see that what it says is that it's the magnitude of the static friction maximum. So it's basically the maximum possible static friction that you can get before it breaks and the object is able to move. So only in the case that the object is just about to move can we relate the static frictional force to the normal force with this coefficient, which again is a property of the two objects, of their rubbing contact. So we'll see how that works, but basically what it's going to mean is when you do a problem, you're only going to be able to plug this result in if the object is about to move. So there could be static friction when the object is not moving, and then you can't use this equation. It's different than the force of kinetic friction, where if I wrote down Newton's second law, I would just be able to write down the magnitude of the force of friction in that equation, and then I would replace it with mu k Fn at any moment in its motion. Okay, so that's the magnitude of the force of static friction. In the direction, it's not quite as clear as with kinetic. With kinetic, it's just opposite to the velocity. For static, it could sort of be in any direction. It opposes the eventual motion. So it could be pointing sort of in either direction as long as that's what is opposing motion. And we'll see it in a couple of examples. So just a first quick example, let's say that you want to push on your refrigerator. I say refrigerator because refrigerators are often quite massive, right? So here's your refrigerator sitting on the ground, and here you are trying to push on it like this, and it might be that your refrigerator does not move when you try to push on it. So if we do a free body diagram for the refrigerator, it will have a pushing force. However, the acceleration is equal to 0, meaning the initial velocity was equal to 0 and the final velocity was equal to 0, so the change in velocity is equal to 0. So that refrigerator just sits there. Well, this is what we call an inconsistent free body diagram. The sum of the forces is pointing rightward. I guess I could include the vertical forces, but that won't change the problem. So there's going to be a normal force and a gravitational force. The sum of the forces still points rightward here, and yet the acceleration does not point anywhere at all. It has a 0 value. So it must be that there's another force pointing in this direction, and that is what we call the force of friction, or the static force of friction. And you notice that I've drawn it such that the length of the force of static friction is exactly equal to the push. So this shows you that it wouldn't make any sense to be writing down an equation like this for the magnitude of the force of static friction, because the force of static friction is simply equal to whatever you push on it. So you get to choose what the force of static friction is going to be. It's going to be whatever you push on the object with. Now at some point you might be able to push harder, so let's draw it again. So let's say acceleration is still 0, but you decide to push harder on it. Bigger force, and maybe it still doesn't move. So we still have an acceleration of 0. So if that's true, then you get a bigger force of static friction. It must oppose it. It opposes the motion. It opposes the relative motion of the two objects, which are the refrigerator and the ground. So the motion of the refrigerator relative to the ground. Now at some point, you could push even harder. So let's draw one last picture. Oh, I guess it's not in my clipboard. Maybe this was about the maximum force, and so you give it just a tiny little bit of a push further. And what happens? Well, the static frictional force goes to 0, and the thing starts to accelerate. And it starts to accelerate because mu s is almost always less than mu k. So although mu s was holding it from moving, once it starts to move, then the force of kinetic friction is not going to keep it from moving, and you're going to get a smaller force of kinetic friction. So you'll get a kinetic frictional force, the dragging force of the refrigerator across the floor, but the force of kinetic friction will be smaller than the force of push, and therefore the net force will point right, and therefore it makes sense that you have an acceleration that points right. Okay, so we're going to do two examples that exemplify these two forces. This first one is really, it's sort of the canonical example for kinetic and static friction because it's a way of looking at both of them sort of at the same time. So imagine this scenario. You're in the library, you are bored, and you decide to do some physics experiments. So you steal a board out of the shelves. Let's say it's a 2-meter long board. And then you take a book, which is 0.5 kilogram, and you place it at the end of the board. So the setup is like this. So you place this book here at the end, and then you start to raise the board up. So it makes some angle with respect to the horizontal. So what it says is, as you do this, as you raise it slowly, the book just remains there. So it has no acceleration. It keeps its 0 velocity relative to the board. And only at some point, only once the angle gets to 37 degrees, does it then start to slide down. And then they say when it slides down, it takes 1.5 seconds to get to the ground. So given that information, what are the values of the coefficient of kinetic friction and the coefficient of static friction? And remember, these are properties of the pair of the surface of the book and the surface of the board. If you get yourself a slipperier board, then mu k and mu s will probably go down, or same thing if you get yourself a more slippery book, whatever that means. So let's try this out. So qualitatively, we see that there's going to be sort of two things that are happening. So let's just quickly write down what those would be. So qualitatively, we have first the case where you have some angle here, you have a book, and you have 0 acceleration. So the reason you have 0 acceleration is, despite the fact that there's the force of gravity having some component down the ramp, you're going to have a force of static friction that exactly balances that out, and therefore it does not move. So that's what's going to occur in the beginning until you reach that breaking point, the value of the angle. So that would be theta less than what we might call the critical angle of 37 degrees. Now, at the moment that it hits the critical angle, then that will mean that the force of static friction has reached its breaking point, has reached its maximum value. And then after that, so now we can say that theta is equal to the critical point, but the friction has now broken. And in that case, you're going to get an acceleration of the book down the ramp. And you're going to get some time to slide, which was given to us. And the free body diagram looks almost the same. You have the force of gravity, you have the normal force, and you have a frictional force. But that frictional force is now a kinetic frictional force, and it's going to be smaller than it was before for the static, which allows the net acceleration, the net force to point down the board, which by Newton's second law means that the acceleration also points down the board. So this is what happens first, and then this is what happens later once you reach that critical angle at which the static friction breaks. So let's do the later case first, because that might be a little bit easier to look at. So the idea is that static friction has broken, and yet we're basically still at the same angle. So we're at theta is equal to theta critical, which we said was 37 degrees. Our free body diagram for the book, well, let's draw it just in the middle of its slide. So it started out up here. It's going to end up down here. And in the middle of its slide, it has the force of gravity. It has, in fact, everywhere along its slide, it's going to look exactly like this. It has a normal force, and it has a frictional force. So this is the new thing we have today, the frictional force, which it's nice to show when you use a frictional force the direction of the velocity, because you want to make clear that that frictional force points in the opposite direction of the velocity. And in addition to that velocity, we should also draw, because it's a free body diagram, the acceleration vector, which will point down the ramp. So we know it points down the ramp because we're told that it starts to move. It goes from a zero velocity to a downward velocity, and therefore there's an acceleration. And of course, we'll assume it's a constant acceleration in order to solve the problem. So we've drawn a free body diagram. The next thing to do is to sort of shut off our brains and do Newton's second law and see what that gives us. So let's do Newton's second law. So the net force is equal to the mass times the acceleration. And in this particular free body diagram, the net force is the normal force plus the force of gravity plus the force of friction, kinetic, is equal to the mass times the acceleration. That's the end of the physics. We've written down the law of nature, and now we just do our math. We do our vector math. So we have to choose a coordinate system, and since the acceleration is pointing down the ramp, let's point the x-axis down the ramp. So that's my x-axis, and then we'll choose y to be perpendicular to that. And so now we can look at the x motion. So first we rewrite the equation, fnx plus fgx plus f friction x is equal to max. And then we just find each component. So the normal force is this vector. It points along the positive y-axis, and therefore it has a 0 x component. So I put 0. The gravitational force, well, that points in this direction, right? It points downward. So you can see it's going to have a positive x component, and we can find that. We've done it a couple times before for ramps. So here's our y-axis and our x-axis, and here's our gravitational force. So its y component is going to be this negative number, and its x component is going to be this positive number. So let's find that with a triangle. We're definitely going to need another page here. Let's draw a triangle there, but remember we need to find our angle of the ramp in here. So we draw a line that is like the ground, because then we can see that the x-axis has the angle of the ramp, and because this is a right triangle here, this is not the angle of the ramp, which means that this is the angle of the ramp. So I can draw, for example, this little triangle with FG on the hypotenuse. This would be the y side, and this is the x side, and this is theta, the angle of the ramp. So if I'm looking for FGX, then I say, well, sine theta is equal to x over FG, where x is equal to FG sine of theta. And in this case, I've chosen my coordinate system such that that's a positive number. So FGX is just equal to FG sine theta. And I write that, FG sine theta. Okay, now we need the x component of the frictional force. Well, the frictional force points backwards. That's in the negative x direction. It doesn't point in the y direction at all. So we just put minus the force of friction, magnitude. Don't stop at the equal sign, keep going. Now we need to look at AX. Well, the x component of this vector is clearly a positive number. It only points in the x direction, so it's just equal to A, magnitude of the acceleration. So you're still new at this, so you might take a look at these three equations. Vector equation, so the acceleration vector appears here. Component equation, so the x component of the acceleration appears here. And then I replace each component in terms of the magnitude of that vector. So I say, well, the x component is a positive number, which I can just write as the magnitude of the vector. Whereas the x component of the friction was a negative number, but it's exactly equal to minus the magnitude. So that's our main process. Okay, we make a boxed equation out of that. So we have FG sine theta minus the force of friction kinetic magnitude is equal to ma. And that's something that we have to use. Now we do the y equation. So Fn y plus Fg y plus F friction kinetic y is equal to ma y. We go through and look at them. We see the normal force points in the positive y direction. It's going to have a y component that's just equal to its magnitude, so plus Fn. Fgy, well, we see here that it has a negative y component that's going to be minus whatever this y is, but you can see I've done sine, so it must be cosine, so it's going to be minus Fg cosine theta. You should write that out for yourself. And then F friction y, well, that points in the x direction, so it has a 0 y component. So it's going to be plus 0. Keep going across the equal sign. We have mass times the y component of the acceleration, but this acceleration vector points along the x-axis only, so that's going to be 0. So our second boxed equation is that the magnitude of the normal force is equal to Fg cosine theta. So, what does that tell us? Well, what we're interested now is trying to relate the time that they gave us for this entire fall to the acceleration. And then from that, we should be able to find out something about the frictional force. So let's take those things one at a time. So we have a normal force here, and that's exactly what couples this equation to this equation, because the frictional force, remember, is written in terms of that. So let's start with equation 1 there, and let's use the definition of the magnitude of the force of friction. So this is like the only new piece of today's work. Everything else is just playing around with Newton's second law again. So if we use that definition, then we get, well, let's also use the definition of the force of gravity. So we get mg sine theta, and then we have minus mu k Fn, and that's equal to ma. So that's equation 1. But I have an expression for Fn, so I can plug Fn into that equation. So we get mg sine theta minus mu k, and then Fn I can write as mg cosine theta. So again, using the definition of the magnitude of the force of gravity, mg, and that's equal to ma. Now, what do we have? Well, we're looking for mu k. So it looks like I can divide both sides by m. M appears in every single term. and then I can solve for mu k. So let's do it in 2 steps. So adding mu k to both sides, we get mu k g cosine theta plus a is equal to g sine theta. So I added mu k g cosine theta to both sides. And then I can subtract off a and divide by g cosine theta. So we get mu k is equal to g sine theta minus a all over g cosine theta. So our question was, what is mu k? And I now have an equation for it. I'm not quite done, though, because I don't know the acceleration yet. But luckily, I was given information about it. Remember, we were told that in the slide, the book goes from the top to the bottom, and the t-slide was exactly 1.5 seconds. So what is that? Well, that's a kinematics problem. In fact, it's a constant acceleration kinematics problem. I can choose myself an x-axis that points along the ramp that has its origin up at the top of the ramp. I have a constant acceleration pointing down the ramp, meaning directly along the x-axis. And I can do a little kinematics problem. So let's do it. So we say, okay, x is equal to x0 plus v0 xt plus 1/2 axt squared. That's an equation for constant acceleration. I want to go from the origin up at the top to the bottom. So let's state that. I'm going from A to B. And this distance, I can call d, but we were given it. It's 2 meters. So I can write x final is equal to d. You see that that's along the positive x-axis. X initial, well, that's where I placed the origin, so that's 0. V0x, well, it starts from rest. Remember how we got there? We raised up the board until it detached, until the force of static friction broke, and so it started from rest. So this term is 0, and then we have 1/2 the acceleration x component. Well, the acceleration points along the x direction, so that's just the magnitude, a, and then we have t-slide squared. So a is what we're looking for, so we can just solve this for a. So it looks like we get a is equal to 2d divided by t-slide squared. So well, let's just find that number since we can. So that's going to be 2 times 2 meters divided by 1.5 seconds squared, and that's 1.78 meters per second squared. Okay, now we have a number for A. Everything else in the equation for mu k is known. We have g, 9.8, and we have theta, which we said was 37 degrees. So I can just plug in the values for all of those things. So let's do it. 9.8 times sine of 37 minus the acceleration we just found divided by 9.8 times cosine of 37, and we get 0.53 approximately. There are no units to that number. You can see in this equation that we're dividing an acceleration by an acceleration, so we don't get units in that. But you can also see in our definition of the frictional force, we have a force in newtons on the left-hand side, and the normal force is also a force in newtons, so there are no units to this coefficient. So it just turns out that it's 0.53. And we'll usually find that the coefficients of friction are less than 1. So that you can read in your book about why exactly that is. It has to do with the fact that you want the object to be able to move at all, so the frictional force doesn't completely overcome motion. So we found one piece of it. We found the kinetic friction, and we did it by looking at just the part of the experiment where the object was sliding. Remember, this is sliding friction or rubbing friction. So now we need to go back and look at what happened in the beginning, what happened in the first part. So we raise the book up as we increase this angle, and at some moment it breaks and then slides down. What we want to be able to do is use the equation for the force of static friction. But there is no equation just in general for the force of static friction. We only have an equation for the maximum value of the force of static friction. And in that case, it looks like this. So what that means is we need to study only the case in which the force of static friction has reached its maximum value. So that means we look at theta is equal to theta critical. Again, so here we looked at theta is equal to theta critical, but at the moment after the static friction broke. Now we want to look at theta is equal to theta critical just before it breaks, so that there's still a force of static friction. So maybe this is like 37.00001 or something like that in order to get that static friction to break. Okay, so let's do this case here. So we'll go back here and let's redraw it. So we have basically the same picture, but with a couple slight differences. So we still have that we're at the breaking point, because remember we can only apply that nice equation when we're at the breaking point. That means that the book is still up at the top of the ramp, so we don't draw it anywhere else. And what are the forces on it? Well, we have the force of gravity, we have the normal force, and we have the force of friction. In this case, it's the force of static friction. And because it has not yet moved, because the force of friction is at its maximum point but still able to support the book, then we say that the acceleration is equal to 0. So this case looks similar to what we did last time, but it's different. It's not the same free body diagram, which means that it's not the same results that we're going to get. So we need to write it all out again. So we have F net is equal to ma. We have the sum of the forces in this case is normal plus gravity plus static friction. We again choose a coordinate system, and I might as well just choose that same one, x and y. And looking at the x equation, so Fnx plus Fgx plus F friction static x is equal to max. And we go through. So Fnx, well, that's 0 because Fn points on the y-axis. Fgx, well, that's exactly what we found last time. You see it's a positive x component, and it'll be found by the sign. So it's exactly plus Fg sine of theta. And F friction x is exactly what we found last time as well. It points in the negative x direction, but this time it is the static force of friction. And ax, well, ax is 0 because the acceleration is equal to 0. So that's 0. So our first box equation here is that the force of static friction is equal to mg sine theta. Now we can do the y equation. F normal y plus Fgy plus F friction static y is equal to may. Fny, that's positive Fn because it points in the positive y-axis. Fgy is a negative number, and it's just like we found before. It's minus mg cosine theta. And the frictional force has no y component. It points only along the ramp, only along the x-axis as I've chosen it. And of course the acceleration is also equal to 0. So our second equation is that Fn is equal to mg cosine theta. And that was exactly what we found last time. So what do we do now? Well, we want to find mu s, and mu s will be buried in here as long as we are at the breaking point. So we should state all of that. So we assume that theta is equal to theta critical, which we were told was 37 degrees. So F friction static magnitude is equal to its maximum value. That's what we mean by the breaking point. So we might even write that out one more time. So we replace F friction static with F friction static maximum, meaning it's not just any frictional force that's being applied, it's the maximum possible that can occur for that interaction between the book and the board. Now I have an equation for F friction static, and that is mu s times Fn. So I'm allowed to use that equation once I've decided that all of this is true here. And what can I do? Well, I have an expression for Fn, so I can plug that in. So I have mu s times mg cosine theta is equal to mg sine theta. And you can see this reduces very nicely if I just solve for mu s. So mu s is equal to mg sine theta over mg cosine theta. The mg's cancel out. We get sine theta over cosine theta, or you can simplify that to mu s is equal to tangent of theta. And I really should have said here theta critical. So all of these thetas are critical, meaning it's the value at the breaking point. Okay, so what is that? Well, let's plug it in. So what is tangent of 37 degrees? Well, it's 0.75 approximately. So we found it. And notice what we found is that this is a greater value than mu k. Mu k was 0.5. That will often be the case, that the static friction is larger than the kinetic friction. And what that allows is that as soon as it breaks, it can start to slide because mu k is less than mu s. You can look in your book about exactly what causes these forces. Basically, it's the roughness of the two surfaces on the very small microscopic scale. And the static friction can be explained, well, if you take your hands and sort of make little claws out of your hands, then you can see that your knuckles are sort of rough, and you can put your knuckles together, sort of mesh them together like a gear, and then you can see that they get stuck in that way. So that's what static friction is. It's the merging of two surfaces, and then it takes something to sort of break them apart, but once you break them apart, then your knuckles will sort of rub against each other, and that's kinetic friction. So you have some sense about what these things are. We'll do one more example, and that's this. So you're still in the library, and you find a library cart on wheels, and its wood, the wood that makes up the cart, is exactly the same material as the shelf. So what you want to do is you want to use the book and do another experiment, and we can assume that mu k and mu s, those are exactly the same because we have the same materials. The question is, how fast do you need to push the cart such that the book sticks to the front? So you understand what's going on here? You're gonna run behind the cart, pushing it, and somebody's gonna place the book on the front of the cart, and you want it to just sort of levitate there. So is that even possible? How fast do you need to go? Do you have enough room in the library to do that? Well, let's see. So let's draw a picture of it. So here you are, running behind the library cart. I don't know why you're off the ground. So here's the library cart. And you're going to be pushing on that thing, and then you're going to put the book right in front of it. And what you want is for that book to just stay right there. So let's try and understand why that might happen. Well, maybe I should draw a little bigger picture here. So we have the surface of the cart. That doesn't make sense. So we have the surface of the cart, and then we have the book sitting there. Okay, so this is the cart here. So let's do a free body diagram for the book. So what are the forces on it? Well, the book has mass, so there must be a force of gravity on it. And you can see that the book is in contact with the cart, and therefore there's going to be a normal force. And at this point, you can see that if you add up those forces, you're going to get some acceleration sort of downward and to the right. So that means the book is going to slide down the surface of the cart, if not just fall off the cart. So how is it that you could make the book levitate there? Well, you need a force that points upward. So what is that force that points upward? Well, if you want it to just levitate there, then that means not only does it have a zero acceleration in the vertical direction, but it must be motionless. So this is going to be the force of static friction. So there has to be a static frictional force there. So now if you add up those forces, you see the acceleration points to the right. So it's not really levitating, but it's accelerating to the right. How does that work? Well, it must mean that it's not how fast you're going, but how much you're accelerating. So in order for this free body diagram to be consistent, we want to have an acceleration that points to the right, matching that the sum of these forces, well, just becomes this normal force pointing to the right. So this is now a consistent free body diagram, and all that's left to check is whether we could actually realize this, whether this could actually happen. So we should make a change to the question, though, because the question was really stupidly worded. It's not how fast do you need to go, it's how much must you accelerate. So cross out all of that. How much must you accelerate the cart such that the book can stick to the front? So the value of your velocity doesn't matter at all. Here's your velocity. Doesn't matter. The only thing that matters is the acceleration, because that's what appears in Newton's second law. Okay, we've drawn a free body diagram. We've been asked this weird question, but luckily we've learned Newton's second law, and we know that all you need to do to answer the questions asked is to do Newton's second law. So we do it. So write down Newton's second law. The sum of the forces is equal to the mass times the acceleration. In this case, the sum of the forces is the static force of friction plus the normal force plus the force of gravity. It's equal to ma. We choose a coordinate system to work with. So it looks like everything's in the horizontal or vertical, so this would be a good choice of coordinate system. And we start to write down our component equations. So the frictional force in the x plus the normal in the x plus gravity in the x is equal to max. Then we have, then we find the components. So frictional force points up, so it's going to have a 0x component. Normal force points right, so it's going to be plus Fn. Force of gravity points down, that's along the y-axis, again, a 0 y component. And then we have the acceleration vector, and the acceleration vector points to the right exactly along the positive x direction, so that's just going to be a there. So our first boxed equation is very simple. It's that the normal force is equal to ma. Maybe you can see where we're going. Remember what happened last time. The point of the normal force is that it gets plugged into a frictional force magnitude. And you can see that you can make a bigger and bigger normal force by increasing the acceleration. Or maybe we should say it the other way around. If you accelerate, what's needed to accelerate that book is the normal force there. So it's going to be connected. Let's write down the y equation. So we have F friction static y plus F normal y plus Fgy is equal to may. So what do we get? Well, we go through and find these components. So the static frictional force, well, that points upward. That's along the positive y. So I just write it as the magnitude of the static frictional force. The normal force, weirdly, points to the right here. So that has a 0 y component. And gravity, as usual, points down, and as usual, that's the negative y. And the acceleration, well, that points to the right, so ay is equal to 0. So our second boxed equation is that the static frictional force is equal to mg. So if this book is not going to accelerate down, we've sort of chosen our free body diagram in that way. We didn't allow for the acceleration to point down at all. If that's going to happen, then it must be that the static frictional force exactly balances the weight. That's what this equation means. Well, the question is how fast. That was the question. Now it is how much must you accelerate? What must your acceleration be? And we need to phrase this in a way that we can use the equation for the force of static friction. So the force of static friction we can write down as an equation at the breaking point. So let's find sort of the minimum acceleration that you need in order to keep the book up, meaning the acceleration when the frictional force is at the breaking point. So let's assume the minimum acceleration where the force of static friction is equal to its maximum possible value. So that's going to be the breaking point. That's going to be the point when it just starts to slide down there. And then if you provide any more acceleration, then the force of friction will be perfectly fine. It will hold it up. So let's look. So in that case, then I can use this as the force of friction static max is equal to mg. And we have an equation for that, which is mu s Fn is equal to mg. But I have an equation for Fn, so I can write that as mu s times ma is equal to mg. And now I can solve for my unknown, which is the acceleration. And I guess I should say this is a minimum, right? If you have a larger acceleration, then you're not going to be able to use this equation to find mu s. But if it's just at the breaking point, then you can find out that minimum value. So if we solve for the minimum necessary acceleration, then what do we get? We get mg over mu sm. So it just becomes g over mu s. Well, we solved for mu s last time. It was 0.75. So this is going to be 9.8 meters per second squared divided by 0.75. The denominator is less than 1, so that means that we're going to have to go with an acceleration larger than a g, larger than 9.8. Well, the denominator is 3/4, so it's going to be 4/3. It's going to be an extra third on gravity, so it should be like 13, but let's calculate it. So it's going to be 9.8 divided by 0.75. So, well, it's 13. 13.1 meters per second squared. So if you want to do this, if you want to run along with the cart, then you need to run faster than gravity in some sense. You need to run so fast that you can accelerate at more than 10 meters per second squared, such that the book sticks to the side of that cart. It might seem ridiculous, but if you've been to an amusement park, they do exactly this. So they rotate a wall, which gives you a very large normal force. You stand in that thing, and the wall pushes up against you, and then the floor drops out, and you're stuck to the wall. So it's possible. You're stuck to the wall because of the static frictional force. We'll talk about that more when we talk about circular motion, but it's going to come down to exactly the same thing. All right, we'll see you next time.